This is Unit 5, Video 3. In this video we will talk about something called the Kinetic Molecular Theory of Gases, or the KMT. Now this theory is a set of rules or statements that describe the behavior of gases and the behavior of ideal gases. So think of the word ideal as perfect. Perfect gases. And we'll assume all gases are ideal. All the gases that we're talking about, they follow this ideal behavior. They behave ideally, behave perfectly. So here they are. There are 4 of these statements or assumptions of this theory. Assumption number 1 says that gas particles move in constant, rapid, straight line motion with an average speed of about 1,000 miles per hour, which is pretty impressive. This is faster than the speed of sound. Now, gas particles are so tiny, and in any container, you have so many of them that they're constantly flying into each other, bombarding into each other, bouncing off of each other, and so they're constantly moving. I mean, the movement is very, very quick, very, very fast, and it feels like there's nothing there because they're moving so fast. They create the illusion that it's a static, it's like a standstill environment, but they're constantly moving. That's how fast they are moving. Statement number 2 says gas particles have no volume. Now what this means is if you have a container with all these gas particles, the volume, the space that the gas particles occupy themselves is so tiny as compared to the entire container that you can say there's really no volume taken up by gas particles. So in truth, for example, you may have a huge container, and if you collect all the gas particles and scrunch them together and put them together in a tiny corner, they'll simply take up a tiny amount of space as compared to the rest of the container. So it'll be safe to say that the gas particles really take up no space at all. That's kind of the idea. That tiny amount that the gas particles are taking up is insignificant compared to the volume of the whole container. So if the volume of the whole container is 10 liters, maybe a tiny, tiny fraction of it is the gas particles. So we can say that gas particles have no volume. That's what this means. And this is why gases can be compressed. They can be compressed to very, very small volumes, or very big volumes as well. This is why they can get compressed. Statement number 3 says gas particles do not attract or repel each other. Now, when particles attract or repel each other, remember, a liquid has particles that are stuck together, or at least they can slide past each other, but they are connected to one another. There's an attractive force between the particles. So this is a liquid. This would be the example of a liquid. Gases, on the other hand, have no attractive forces between them. If they did, they'd become a liquid. That's why gas particles are defined as gases. And then number 4, gas particles have what are called elastic collisions. This is a fancy word, meaning that they don't lose energy when they collide. Regular spheres, if you throw 2 spheres at each other, as they collide in the middle, they'll actually lose the energy. Some of the energy will be dissipated out, and the spheres will slow down. Think of a billiard ball table with, say, you're playing pool, and eventually the balls slow down. That's because their collisions are inelastic, but the gas particles have elastic collisions. They never slow down, they never lose energy, is the idea. Alright, so these are the 4 assumptions. Now, believing these 4 assumptions or 4 statements, we can now describe gases. However, we should realize that real gases follow these assumptions under ideal conditions of temperature and pressure. And then when the temperature and pressure become extreme, then the gas does not behave like a gas anymore. So under extreme conditions of temperature and pressure, this does not work. So think of a gas. You have a container with a gas. If you start to cool this gas to a really, really low temperature, as you decrease the temperature, eventually the gas becomes a liquid. This makes sense. Even oxygen becomes a liquid at a lower enough temperature. And if it's a liquid, it's no longer a gas. So that would be an extreme temperature condition, really low temperatures. Another extreme condition would be pressure. If you increase the pressure of this system, then you're essentially forcing the molecules together, and as you're forcing them together, the molecules stick to one another, and they become liquid. They're no longer gases, and that's why this breaks down at high pressure and low temperature. In fact, you can liquefy a gas by either decreasing the temperature or by increasing the pressure. Oftentimes you have to do both. You have to both increase the pressure and decrease the temperature to liquefy a gas. Alright. Alright, so let's try applying what we've just talked about. Example 3 says, which of these statements describe ideal gases and which describe real gases? So A says, at low temperature, gas particles stick to one another and become liquids. Well, this is with real gases. Real gases do this. If you cool them down, they'll eventually become a liquid. Ideal gases are perfect gases that never become a liquid. So this is just describing a real gas, like oxygen or nitrogen or really any gas. B says at very high pressures, the volume of gas particles must be taken into account since there are so many of them in the container. So, at very high pressures, what happens is you have very high pressures because you have a lot of gas particles. One way to increase the pressure is by really keep pumping gases into the container. The more gases you pump into the container, the more the pressure will build, and eventually you've got so many gas particles that they take up a significant part of the container. If you squeeze them all together into the corner, now they're going to take up maybe this much of the container, which means you have to consider their volume. Now, this is not true of ideal gases, so this must be describing real gases again. This is a real gas. A real gas has volume. An ideal gas does not have volume, and that's the idea. Alright, so try the same thing with this practice problem. It's really just going through those 4 facts, 4 statements. And this is a short video, and we'll do video 4 over gas laws.